Okay, so what I would like to tell you about is this a billiard story. So I guess that everybody here knows what is a billiard. And maybe something which is a bit less known is what combinatorics has to do with billiards. Okay, so that's what I would like to explain. And there is one thing that I would like really to spend a bit of time on is this tree inequality by Penrose, which is a very important tool in combinatorics. And I think it's a very nice and elegant proof. Also, it's very simple. So that's why I think it's very suitable for this lecture. Okay, so I will start by talking about random balls. And even simpler, I will start with random points. Okay, so here I guess everybody has learned a lot of things about integration. So here this one will not be very complicated. So the question here, so the first question is what is the probability of a random configuration of endpoints? Okay, so you have a domain. You would like to put at random endpoints in this domain, okay, and compute the probability measure which is associated to this operation. Okay, so here you see it's really simple because what you would like to do is to just put the Lebesgue measure on this, say, on the tensor products of A by A by A by A. Okay, so if you have this square here A, then you see that the probability of having x1 in this square, x2 in this rectangle here, x3 in this rectangle, and x4 in this rectangle is just the product of all surfaces. Okay, so that's very simple. It's just a Lebesgue measure. It's okay. So now there is something which is a bit more complicated. Is the case where you don't know in advance the number of points. Okay, so now I would like to pick at random n points, but n is also a random number, and so that's what is called in statistical physics grand canonical setting. Okay, so that's the canonical setting. You just pick randomly the endpoints, and now the number of points is also a random variable. And so you see that there is a very classical law, which is the Poisson law, where you assume that the probability of having endpoints is just exponential of minus mu times mu to the n divided by factorial n. Okay, so this tells you that the average number of points, say in average, the number of points should be mu. Okay. And then you can put this, say, once you know this number of points, then you can pick the Lebesgue measure on the space A to the n. Okay, so that's how you can define a random configuration of points. Okay, but now I'm not interested in points because in the end I will be discussing billiards, and so I'm not interested in points but in balls. Okay, so that's the next step here. And at the moment, so it's not really a billiard because everything will be stationary. So I will pick a random configuration of balls, but once forever. Okay, so it's almost the same because, of course, if you the size of the balls is prescribed, then you only need to prescribe the position of the center. Okay, so you could say, okay, so prescribing n balls is the same as prescribing n points, except that you see that now you have a constraint, an additional constraint, that of course you cannot have an overlapping between two balls like this. This is a configuration which is not admissible. Okay, so now it will be a bit more complicated because you have what we will call exclusion constraints. Okay, so essentially we would like to do almost the same. Okay, so picking the center x1, x2, xn randomly, but now you have to just exclude all this configuration where two centers are at a distance less than, say, epsilon, if epsilon is the size of the ball. Okay, so if you do that, you see that you end up with a probability. So first I define the canonical probability where I've already fixed the number of particles, which is here. Okay, so you see that the probability of that's your distribution of both, say, the distribution of centers in this AN, it will be, so this is just a normalizing factor. And then I say integrate with respect here to the Lebesgue measure, but I have to condition by the fact that I have this indicator function which tells me that all centers are at a distance at least epsilon from each other. Okay, so now I have that this partition function is just a normalizing constant for this to be a probability. Okay? So, and then of course you can have the counterpart at the ground canonical level just by saying that also the number of particles is a random variable, and then you get the same, so you still have just one normalizing constant, which will be also called the partition function. And then you have this, which is reminiscent from the Poisson law, so mu to the n divided by factorial n, so that in the end you expect more or less the typical number of particles to be mu. And then you have this Lebesgue measure, okay, which is just modified by this exclusion condition. Okay, and then there is a very simple question to know whether this probability measure looks like the probability measure that you got for points. Okay, so a priori what you would expect is that if the size of the particles is very, very small, then it should be almost the same to pick random points or to pick random balls, because, okay, you don't expect this to be a very strong constraint if epsilon is very small. Okay, so that's our starting point, and now I would like to answer this question, whether this is very different or not. Okay, so one way you can see whether it's different or not is if z, this constant, this normalizing constant, is close to exponential of minus mu or not. Okay, so that's how we will characterize the fact to be close or not close to the other measure. So now you see that, of course, there is no uniform answer to this question, because there is something which is clearly obvious, that if the size of the particles is really big, and that you have a large number of particles, you have a problem. Okay, so now it's if you have a volume 1, okay, and very large number of particles, and these balls are not very small, then of course there is no configuration which is admissible. Okay, then you can say, okay, maybe I will not take this size to be so large, but maybe still a bit large, and then you end up with something which is called a sphere packing problem. So what is the optimal configuration? Or what is the optimal density that you can obtain by packing these spheres? Okay, so in dimension 2, you can see that this one is not optimal, and this one is much better because there is less empty space. Okay, but this is not at all the kind of regime that I will look at. The kind of regime that I will look at is the regime of what is called dilute gas. Okay, so the regime where epsilon is really small. Okay, so in particular, if you multiply mu, which is the typical number of particles, by epsilon to the d, which is the volume of one particle, okay, up to a constant, okay, then I expect this number to be small compared to 1. Okay, so I don't have really a problem of putting all the particles in the volume, but still it could be a different measure. Okay, so that's what I would like to understand. So in this dilute regime, is it true that say the random balls are distributed almost like the random points? Okay, that's the question. And we will see that in general, the answer is that it's not really true. Okay. Okay, so I will start with a very I will try to start with something a bit intuitive. Okay, and we will see that it's maybe not the best way to proceed, but at least it's a very natural way to proceed. Okay, so what I would like to understand is this indicator function that all centers have to be at a distance at least epsilon. Okay, and so what I would like to say is that, okay, if epsilon is almost 0, then this indicator function is almost 1. Okay, so I will just write this equality here, that being at a distance bigger than epsilon is 1 minus the fact that xi minus xj is smaller than epsilon. Okay, and this, say, to have a short notation, I will just write that this condition, which is actually the overlapping condition, okay, that the two balls are overlapping, I will use this short notation for this overlapping condition. Okay, so now, of course, I don't have just one. If I have just one, and then it's easy to see that if you take the L1 norm of this guy, of course, this is like epsilon 2 to d, and so it's true that this guy is very close in L1 norm, okay, to 1. Okay, but now, of course, I don't have just one of it. I have a product of such factors. Okay, and so I would like to use this this decomposition here. So now I have a big product with many terms, like 1 minus the indicator that I is close to j, and I would like to expand this product. Okay, so that's a very natural way to proceed. Okay, if you have 1 minus epsilon times 1 minus epsilon, what you would like to say that it's 1 minus 2 epsilon plus epsilon square. And so essentially it's like 1 minus 2 epsilon, because epsilon square is still much smaller. Okay, so I proceed exactly this way. So now I have 1, and I'm very happy with this one. Okay, then I have the sum for all couples I and j. That's I is close to j. Okay, this one is fine as well. Then I have the sum over two couples that both of, so I have I1 close to j1 and I2 close to j2. And then I have the same, so I have, of course, the alternance of plus and minus sign. Then I have this minus, and then here I have a sum with 3 couples. Okay? And so I will just explain the problem with this term here. Okay, so you see that, of course, if I1 is close to J1 and I2 is close to J2, okay, and I1 J1 is different than the pair I2 J2, then you see that, of course, this in L1 norm, if you integrate, okay, you have 2 constraints, and so you expect the L1 norm of this guy to be of the order of epsilon square. Okay, so that's good. This term is good. Now, if you have 3 of them, then you see that it's different, because you can imagine that I1 is close to J1, I2 is close to J2, but then maybe you can choose, say, I3 to be J1 and J3 to be J2, and then you see that you will not have any more constraint. So this means that actually you have a product of 3 terms like this, but actually you have only, say, 2 conditions which are really independent. Okay, so that's very bad actually. Okay, because this means that this term, of course, you have a lot of them. Okay, because you can pick 3 couples at random here, but then you see that you have only 2 conditions. Okay, so the L1 norm of this guy is not like epsilon 3, it's like epsilon square. So this means that this kind of expansion is not very good. Okay, because say I will have many terms, and if I look at the term of order 4, I will have the same problem, and so these terms are not really ordered. Okay, so that's a bad expansion. So now I will try to explain that the good expansion is the expansion where instead of expanding directly the partition function, I will expand the logarithm of the partition function. Okay, so the result here is simple. So the result is not very complicated, but then I need to explain how you get it, and I will try to do this proof in details. Okay, so what I say is that if I expand the logarithm of the partition function, so recall that the partition function is just the integral of this product, okay, which is supposed to be 1 plus correction for the order of epsilon plus correction of the order of epsilon square and so on. Then what I obtain is that it can be expanded as sum over n of mu to the n divided by factorial n. So this comes from the grand canonical setting. And then here what I have is what is called a cumulant. Okay, phi n here is a cumulant. So this cumulant is 1 if n is equal to 1. Okay, it's not really interesting. And say as soon as n is larger than 2, the way you obtain this, the way you can represent this cumulant is by taking all graphs which are connected of order n. So now you see that you will have at least n condition. Okay, so this means that x1, x2, x3, xn here. Okay, so if you are on the support of phi n, okay, you have something like this. So I will just call this 1, 2, 3, n. And what I know is that I have a graph like this. Okay, so maybe it's not minimal. So for instance, this one is not minimal. You see that this condition here is not independent from this one and this one. Okay, but at least all vertices are connected. Okay, so being a graph in Cn means that the graph is connected. Okay, so if the graph is connected, of course, what you expect is that if you compute the L1 norm, okay, you can extract from all these constraints at least n-1 constraints which are independent. Okay, so you have n-1 independent constraints. And so you see that this expansion is much better because you expect phi n in L1 to be like epsilon to the n-1, or epsilon d to the n-1. Okay, so that's the size in L1. Okay, so this means that here you don't have the what I had previously, so it's really a much better expansion. Okay, so actually we will try to estimate very precisely this phi n, but here for the moment what I just give you is the definition. So the definition is that you have the sum of all possible graphs which are connected with n vertices. And then you take the product. So each time you have a vertex here, this means that you have this condition that 1 and 3, for instance, here, or I and j should overlap. Okay, and you have this minus sign. Okay, so that's just the definition. Okay, and now, of course, I have to prove this formula because it's, okay, I have to prove something. Of course, the log of mu was already defined, and then I have to prove this. Okay, so, but you see that at least it's expected to be much better because you have really this ordering of the different terms. Okay, so let me explain how you can prove this thing. It's not the proof that I would like to really insist on, but this one is okay, maybe interesting as well. Okay, but there is a bit of computation here. So for those of you who are not really familiar with series expansion and analytic function, maybe you will be a bit unhappy, but okay, it's not really complicated. Okay, so I start from this z mu. So the partition function itself is just this big product. So maybe I should write it. Okay, so z mu. So this is the integral. And then you have this product that of 1 minus, okay, for all possible pairs ing. Okay, so that's what you would like to expand. Okay, so now you see that, and okay, then there is this factor. Okay, of course, there is the mu. Okay, so that's for n fixed and then u. But now you see that when you expand this guy here, you see that essentially you will get all possible graphs. Okay, not necessarily connected, but you will get all possible graphs because when you have one, then you don't have the vertex, and when you have this, you have the vertex. Okay, so for each couple of vertices here, either you have the vertex or you don't have the vertex. So in the end, you can reconstruct all possible graphs. Okay, so that's how you proceed. And now, what you would like to do is to decompose. So if you start from any graph, of course, you can decompose it in connected components. Okay, so that's what I do here. Okay, the pointer is not really. You see something? Ah, oui, here, see, it's here. Okay, so you decompose the graph into connected components like this. Okay, and then you compute. Okay, so that's not really interesting, but essentially, that's this computation here. So M1, M2, M3, M4, Mk are the size of the different connected components. Then you have to choose. So you have a combinatorial factor, which corresponds to choosing, say, how you group the different connected components. And then inside each connected component, of course, you have this sum over all possible connected graph of this. Okay, so that's really something that's, okay, maybe you need a bit of time to do the computation by yourself, but really there is no difficulty here, okay? You just rewrite this thing here, okay, by expanding everything and just decomposing each connected component. Okay, and here you just need to compute how many ways you have to decompose the same with the same connected component. Okay, and then here you recognize this expansion with the 1 over factorial k of this guy. Okay, and so here you recognize so probably so this is of course something to the power k, and so this is the expansion of the exponential. Okay, so that this tells you that the z mu is the exponential of this guy, and so that's exactly what I told you on the previous slide here. So you have this expansion here with this definition of the cumulant. Okay, so once again, it's just a bit of computation. It's not very funny, but okay, it's just use the series expansion of the exponential and logarithm. It's not really. The only thing that you need to understand is that really the important point here is to decompose the graph into connected components. Okay, so that was the cluster. So you see that this means that a cumulant is associated to a cluster. Okay, a cumulant tells you that if I have cumulant here phi n, this means that 1, 2, 3, and n are in the same cluster. Okay, so that's it was before COVID, and it's already the notion of cluster. Okay, so now that we have cluster, we will look at trees. Okay, which is another important notion in combinatorics. Okay, so what I would like to do is to start from this formula, which is here. So of course, I told you that essentially I expect this phi n in L1 norm to be of the order of epsilon d to the n minus 1. But of course, this is, say, the size of one realization. Okay, if I have one realization like this, okay, what I expect is that once I have fixed this graph here, I expect that the L1 norm of this term is of the order of epsilon to the d times n minus 1. But of course, you have many realizations, because you can have any graph which is connected of size n. Okay, so if you count just very roughly the number of connected graph of size n, then you end up with a big number, and there is no chance that you can sum this series here. Okay, because of course the number of a connected graph is much bigger than factorial n. Okay, and so there is no chance that the series here is convergent. Okay, so if you do that and you just estimate in a very rough way the number of connected graphs, then it's the end. Okay, you cannot do anything with this formula. Okay, so now you need to be a bit more subtle, and that's what I would like to explain here, is how you can be a bit more subtle, and just also remember that, of course, you have all possible graphs, but you have signs. Okay, each time here you have an edge, you have a minus sign. So for instance, this contribution here, because you have 4 edge, will have a plus sign, while this one will have a minus sign. Okay, so maybe you have some kind of compensation. And of course, you need to use this compensation, else the series will never be convergent. Okay, so that's exactly what I would like to explain here with this partition scheme and these trees. Okay, so I start from this definition. Okay, so the definition that phi n is, if you remember, maybe I should write it. Okay, phi n is the sum over all possible, is defined with a sum over all possible connected graph, the product of ij, which is an edge of g, of minus this indicator function. Okay, and so what I would like to do is really to take advantage of this minus sign. Okay, and so what I say is that actually you can prove this tree inequality, which is due to Penrose and which is really a nice inequality, which is really useful in many, many problems of combinatorics. Okay, and so you see that the absolute value of this guy can be estimated by the sum, but now you see that instead of summing over all possible connected graphs, you will just sum over all possible trees. So what is a tree? A tree is just a minimal connected graph. Okay, so meaning that it has exactly n-1 edges. Okay, so you see that, of course, there are much less trees than connected graphs. Okay, essentially, if you have a tree, you see that essentially you have a factorial n, okay, which is much better. Okay, and then you see that you have the same product over all edges of this indicator function. Okay, and of course now you have no minus sign; everything is non-negative. Okay. So the good thing is that the cardinality of the set of all possible trees is not factorial n. Actually, it's given by the Cayley formula, and it's n to the n-2. Okay, this is something that you can prove recursively. Okay, it's kind of easy recurrence. Okay, but you see that if you remember, Stirling's formula tells you that factorial n is also like n to the n up to this correction here. But you see that when you take the quotient of this guy by this guy, you get something like e to the n. Okay, so that's a geometric sequence. And so you can expect that this series in the end will be convergent. Okay, so that's really important that the cardinality of the set of trees is not exactly like factorial n, but factorial n times a constant to the n. Okay, so that's why it's important to prove this inequality. Okay, and so I would like to spend essentially the remaining time, maybe less, keep some minutes in the end to explain the link with billiards and all these kind of things, but I would like to spend a bit of time to prove this formula here. Okay, so this really, once again, I would like to insist on the fact that it's really a very important tool for many problems in statistical physics. Okay, so all the problem of phase transition, things like this, they are really, they are often related to this identity here. Okay, so actually this is a proof which is very nice because there is almost no computation, so I like it. Okay, so it's a very, I think it's a beautiful construction. Okay, so now the idea is to construct what is called a partition scheme. The partition scheme, the idea is just mapping between the set of all connected graphs and the set of trees. Okay, so I would like to have just this scheme sending all trees, all connected graphs on a tree. Okay, so I would like to explain how I will construct this tree. So, and the good thing, so you see that if so this mapping pi, you see that if you look at the pre-image of one tree, essentially, you see that the edges of these graphs, of course, they should contain all the edges of t. Okay, so you don't expect to send this graph here. Okay, it's something that is, I think, is clear for everybody. That so this is a graph. Okay, this is my G, and I would like to send this on a tree, so on something which is minimally connected. And of course, I will not do something like this. Okay, this would be a bit silly because this edge here was not present here, so it's completely silly to do something like this. So I would like maybe something like this. Okay, so that's so the first condition, of course, is that the set of edges of T is included in the set of edges of G. Okay, so that's the first condition. And now I would like also to characterize all the missing. Okay, so now you see that here, this is the missing edge. And I would like to be able to characterize all possible missing edges. Okay, and so that's what is written here. Okay, so we can characterize all possible missing edges by this R of T. Okay, so At this point, this is a bit, okay, I think a bit complicated to understand, but now you will see that with the procedure, it's very simple. Okay, so I start with a graph, okay, which n vertices, and I will define the image T in a recursive way. Okay, so first of all, I decide that, for instance, particle, say, vertex number 1 is the root. Okay, so I start here. So this will be the root. Okay, so this is completely arbitrary. Okay, you can fix this one to be the root. You can do whatever you want, but say the pi will be defined once you have fixed this root. Okay, and so now I will keep all edges which are connecting one to something else. Okay, so this means that this one will be kept. Okay, because this is the root. Okay, then I have other parts. So now I have other vertices which are just the kids of this root. Okay, and I will keep all the edges which connect these kids to other vertices, provided that it will not create a loop in the graph. Okay, so here it's simple because I will keep, so of course this is not this one. I will keep this one and this one. Okay, and of course here it's a bit simple because I have only 3. But you see that this one, I will never keep it, because if I keep it at some point, you see that I have a loop in the graph. Okay, so you see that actually, of course, on this example, it's a bit too simple. But say here you have the description of how you proceed. So you fix the root. Then the first generation of T is just a set of vertices which are directly connected to 1. Okay, then the second generation is the set of all vertices. And then you see that you have to order the first generation. Okay, so this means that if this one is number 2 and this one is number 3, this is the first kid. So I know here there is no, okay, just 1. Okay, so if this is 2 and this is n, this is the first kid of this particle, and this is the second kid. Okay, so I keep the order. Okay. Okay, and so I just remove all the vertices, which are all the edges, such that it would create a loop. Okay, so I have the second generation, and of course I can order all the vertices in this second generation, and then I do the same for the third generation, and so on. Okay, so of course there is something which is clear, is that in the end everybody is connected. Okay, because I start from a graph which is connected, and so if I keep all vertices except the one which create loops, then I should end with a graph which is connected, and by definition also it's minimal. Okay, so it tells you that with this procedure, of course, you see that you will not say it's really a mapping. You define a unique tree, and this is really a tree because it's connected and minimal. Okay, so that's the easy part, and of course you see that all the edges of T are edges of G. Okay, so here you have a picture which is a bit more complicated than here. So you start with 1. You see that 2 and 4 are the kids. Then for 2, the only kid is 10. Okay, and for 4, you have 2 kids which are 6 and 9. Okay, of course you don't see these edges, this edge between 2 and 4. So this one, it has disappeared because it would create a loop. Okay. Then you have for 10, you have only 1 kid, and for 8, only 1 kid here. And then for 4, you have 6 and 9. And then for 6, you have these 3 ones, and then you have 9. Okay, so you get this tree. Okay, so is it clear for everybody, this procedure to construct the tree? Yes? Okay, so now something that's a bit more difficult is to characterize all vertices that I have erased in this procedure. Okay, so that's the next step. Okay, so that's how I would like to characterize this R of T, because I said that I would like to say that all the edges here should be so either edges of T or so this R of T. Okay, so this means that this guy should be completely characterized in terms of t. Okay, so now you have to be a bit careful. Okay, so I imagine that I have an edge. Okay, say connecting the vertices I and j, and which is erased in the previous procedure. Okay, so ij is a bad vertex. Okay, a bad edge. Okay, so the first remark is that the generation of I and the generation of, so you can always assume that, say, the generation of I is less than the generation of j up to just exchanging I and j by symmetry. Okay, so that's a completely free assumption. This one, where it is, yeah, this one is completely free. Okay, that's just up to a symmetry. That's okay. And so now the first important remark is that the generation of j is less than generation of I plus 1. Okay, why is it true? Because if the generation of j was bigger than generation of I plus 1, this means that you shouldn't have erased this this vertex because j should be a kid of I. Okay, so if j, so you see that you don't have choice. Okay, so if you have j in your, if you already have I in your tree at some point, and now you look at all possible kids of I, so j should be a possible kid of j, and the only reason for which you can have erased this edge ij is because j was, so you'd already have a loop somewhere. Okay, so it's just impossible. So if not the case, then you should keep this guy. Okay, so there is no other option. Okay, so now you see that it's really a very strong constraint, because you find that the generation of I is smaller than the generation of j, which is smaller than the generation of I plus 1. Okay, so now you see that you have two choices. So either they are on the same generation. Okay, so this means that you will essentially erase all possible connection between brothers and sisters. Okay, so all this horizontal connection, they will disappear. Okay, and the other possibility is that, okay, the generation of j is the generation of I plus 1, but then this means that I is already, of course, if this is the generation here, this means that j will not appear in the tree before this generation here. And so this means that the only way you can have this is that j is connected to a big brother of I. Okay, so j, you have something like k here. So k is the same generation of I, and k is a big brother of I. Okay, so you don't have choice. Okay, that this is the only two possibilities to erase a vertex, an edge, is that either this is a vertex, an edge, sorry, between two vertices of the same generation, or the connection with a big brother here. Okay? So, and then if you say that now you will take, so now you have your tree, okay, which is something like this. Okay. Maybe something like. What I say is that of course R of t will be the union of all these possible edges. Okay, of course I can always do something like this, and I will obtain a different connected graph. And this connected graph, if I compute everything, is if I compute its image by my mapping, I will get t. Okay, the same if I say have a connection like this. Okay, with so no, it cannot be like this. Okay, connection like this. You see that I have something which is non-linearly connected. If I compute the image by pi, it will be the same tree T, and you see that it's different. Okay, so this provides a complete characterization of this guy. Okay, so this is the set of edges between two guys of the same generation, or between a particle here and an uncle which is younger. Okay, so this one, this one or this one. Okay, so this is the complete characterization. So now you have classified all possible connected graphs with this partition scheme. Okay, so that's all the edges that you can remove. So edges inside a same generation are edges towards a younger uncle. Okay, and so now we have that if you take any graph with edges which satisfy this guy, so here it should be the edges of G, of course, then you get, so this exactly describe all possible connected graphs. Okay, so now, okay, what is the connection between this and the rest of the story? So you see that it's actually a very simple computation. You see 3 lines. It's the maximum that I can do right now. Okay, so this is the definition of phi n, a cumulant. You have here the sum over all possible connected graph of this quantity here. And now I will just split this set of connected graphs according to their image by this partition scheme. Okay, so T is the image, and then I, of course, sum over all possible graphs which are in the pre-image of T. Okay, so that's just a partition. Okay, I have all possible trees, and now I know that for each tree I can describe all the pre-image of this T. Okay, so of course this is an identity here. So now you see that you will sum over all possible graph here, and now you see that you split the edges of G in the edges of T and the edges of the rest. Okay, so this R of T here. Okay, and so, but you see that when you describe all the pre-image of T, you will get necessarily all these edges, but this one, they can be or not be in the set of edges. So you have all of this. So here you have all the edges of T, and now for the others, you have the sum of all possible choices here. Okay, so either you pick the vertex, the edge, or you don't pick it. Okay, so when you recombine all this, what you obtain is just a product over all these edges here of 1 minus this indicator function, and of course the product of 1 minus the indicator function, it's always less than 1. Okay, so this factor now is less than 1. This, you just don't care about the sign, and then you end up with this tree inequality. Okay, so with this partition scheme, you can prove very easily this estimate, and you see that it's really very powerful because the number of connected graphs is much bigger than the number of trees. Okay. Okay, that's what I would like to tell you about this partition scheme, and now maybe I have a bit of time to go back to the billard, because it was a bit like the advertisements for this talk. So now I should tell you something about billard. Okay, so first of all, I have to conclude about this story of random balls. Okay, so that was my question at the beginning. So now I have this log of the partition function. What I would like to know is whether it looks like a bit like the log of the partition function for random points. I recall that for random points it's just mu. Okay, it's minus mu. Maybe there is a minus missing somewhere, I guess. Okay, so now I have this. So this is just the formula where I have this. So the first formula that I proved, okay, where I have this expansion with cumulants, okay. So that's the cumulant, and now this cumulant I can estimate its contribution. Okay, so using the fact that the L1 norm for a given tree is like epsilon d to the n minus 1. Okay, because all these constraints, now if you have a tree, of course, all constraints are independent. Okay, so for instance, if you have this tree here, you see that, okay, you fix this point, then this condition, and this condition, they are independent of each other. So each time you integrate respect to this variable, you get epsilon d for this one, and epsilon d for this one. Okay, so you get epsilon d n minus 1 time. Okay, so that's the size of the constraints. And now you have the size, okay, you have the number of trees divided by factorial n. And this, I told you that, say, up to this factor e to the n minus 1, you get a correction here, okay, which is not really important. Okay, so you see that actually the very important parameter in this story is E, which is just E, okay, times mu, which is the typical number of particles, times epsilon d, which is the size of the particle. Okay, so this means that even though the volume, okay, the total volume occupied by the particles is very small compared to 1, okay, this will be convergent, okay, so because this is just like a geometric series. But you see that when E times mu times epsilon d is of the order of 1, then you have something like a phase transition. Okay, so you lose the analyticity of this function, and so something strange should happen. Okay, this doesn't tell you that it's not possible, or I don't know, but so that's the first thing. So you have the problem of this analyticity with respect to the dilution parameter. Okay, and then there is another thing, which is that even though this series is convergence, it's not like 1. Okay, it's not. Say in general, there is no reason why it should look like 1, and so you see that it's really different. Okay, it's exponentially small. Okay, so actually, it's say the two random distributions are clearly different because it's not like 1. Okay, so that's what I would like to tell about this random distribution of balls. Okay, so actually, once you know this partition function, you can say much more, of course, than just computation. You can, for instance, compute the correlation between two particles. Okay, so you can, for instance, say what is the joint probability of finding a particle, so a ball with center x1 and another one with center x2, and so you can compute just by differentiating this partition function, and so you have you can, okay, I will not do this computation here because it's a bit okay, it's not really interesting, but just go here to the conclusion. So the conclusion is that, of course, you get that if x1 is closer of x2 than epsilon, of course there is a problem. You should not have any overlapping. Okay, so that's the correlation here. But here you can also prove that actually you have exponential decay of this correlation. Okay, so because this guy here, so I have not time to explain all these things, but really using this partition function, you can prove that this correlation decay exponentially if you are far from each other. So if you pick just two balls just far away from each other, it's almost like they were not correlated. Okay, so and actually there are many other properties that you can deduce from this partition function. I will not. Okay, so now what I would like to do is to tell you things about, say, the dynamics of, now you have all these balls, but now just instead of looking them just at equilibrium, you would like to have them just moving. Okay, so that's of course closer to billiard than just these stationary balls. Okay, so the dynamics here is very simple. So you have all these small balls. They just move with uniform rectilinear motion until they collide with another ball. And when they collide with another ball, this is just like the classical billiard. They will be reflected and just keep energy and momentum. And so you have this law of reflection, which are the law by Descartes. Okay, so they're really natural dynamics. which is actually Hamiltonian, for those of you who know this notion of Hamiltonian. And so since it's a very, it's a bit singular because the interaction is just by collision, but say it's like a very nice dynamics, and you have this recurrence by Poincaré and so many properties. You see that there is one thing which is not very nice, is that if you change just a bit the position of this one, okay, so for instance you push it here, maybe they will never collide, okay, and so the dynamics will be completely different. Okay, so this system is a very nice system in the mathematical sense, but it's also very unstable. Okay, if you have very small balls, you see that just changing a bit the position of one ball can just change the whole thing after a short time. Okay, so that's really unstable. Okay, so now I have the same question. Okay, I would like to understand the correlations between these balls. Okay, but now, of course, it's more complicated because they are not correlated once forever. They can be correlated because of the dynamics. Okay, so that's still a very active field of research. Okay, it seems that it's a very simple problem because you have only these balls just with rectilinear motion. But still, it's because of this instability, it's very complicated to understand what happens when the number of particles is very large. Okay, and this is a very, of course, it's too simplified, but still it's a good model for gases. Okay, because you can think of all these balls being atoms, and then the gas is essentially this collection of atoms which move and collide or interact each other. Okay, and then you expect the correlation in the gas to be, to behave a bit like the correlation in this system of balls. Okay, so now you see that the measure, so the grand canonical measure here is a bit more complicated because you don't have only the position, you have also the velocities. Okay, so now there is an equilibrium measure which will be invariant by the dynamics, which is this one. Okay, so you recognize here the exclusion. Okay, of course, because you prescribe that the dynamics have collision. You expect that these balls will always remain at a positive distance. Okay, so you get this condition here. Then you have here what is called the Gibbs measure or Boltzmann-Gibbs measure here, which tells you that you take the exponential of minus beta over 2 that times the total energy, which is just the sum of the square velocities, the velocity squared. Okay, so this, you see that each time you have a collision, since the energy is preserved, this guy will be invariant by the dynamics. Of course, this one is also invariant. And then you have this number here, which is just reminiscent of this Poisson law. Okay, which tells you that you have the grand canonical measure and then this normalizing factor. Okay, so this measure here is an invariant measure, so it will not change with time. If you start with a distribution of configuration, which is given according to this measure, then forever, so of course each configuration will change with time, but the measure on this configuration will stay invariant. Okay. So now there is a very specific scaling, which is the scaling which is relevant for gases, for perfect gases, where essentially the number of particles and their size are related by this scaling relation here. And actually it tells you that you expect each particle to have one collision per unit of time. Okay, so you expect to see really a combination of the transport of particles and say once per unit of time, more or less randomly, each particle will have a collision and will be deflected. Okay, and then there was a proof by Lanford, okay, something like 40 years ago, which proved that if you look at the empirical measure of these particles, so you just put a direct mass each time you have a particle, and then you average this. Okay, so for those of you who know a bit about the law of large numbers, you see that it's really something like, so you have random variable here, and then you sum over all possible So this series of random variables, so it's really something like a law of large number. And then you can prove that this guy will be, say, very close to the solution of the Boltzmann equation. Okay, so the Boltzmann equation is a very fundamental equation of which predicts, for instance, the second principle of thermodynamics, and which is used to predict the behavior of gases. Okay, so that's tell you something about the law of large numbers, but now we can also work on the central limit theorem for this but correlation, like we saw for the system with stationary, which is stationary. And so we can also say things about this fluctuation. Okay, so now you look at this measure here. So like in the central limit theorem, you have your random variable, your sequence of random variable. You look at the sum. You remove the expectation. So here the expectation is just this stationary state. And you multiply by square root of mu. So here I recall that mu is the typical number of particles. So it's my parameter in my law of large number. So you can recognize this quantity here. It's just a fluctuation. And now we can, so using this kind of tree inequality and a bit more, of course, we can also characterize this fluctuation. Of course, this is much closer to a billiard and to gas dynamics, so a bit more interesting for physics. Okay, and then we can completely characterize this fluctuation field and prove that it converges actually to the solution of a stochastic PDE. Okay, so probably this is something that you never saw before. Of course, I will not introduce stochastic PDEs now, but it's really a very interesting topic as well. Okay, so you see that in the end, everything is more or less connected. So combinatorics, probabilities, PDEs, and also physics. Okay, so the only thing that I can tell you is that you should learn as much as possible during the master, and then there are many interesting problems. Okay, I think I will stop here, and I thank you for your attention.
Merci beaucoup. Alors, est-ce qu'il y a des questions dans la salle ? Allez.
Alors moi j'ai une question sur les cumulants. Vous avez développé en cumulant le log de la fonction de partition. Et en probabilité classique, il y a des cumulants en développant le log de la transformée de Fourier. Est-ce qu'il y a une théorie unifiée des cumulants ?
C'est les mêmes.
C'est les mêmes.
C'est les mêmes.
Donc la distribution... donc,
en fait, ce qui se passe, c'est que quand on regarde, je pense que c'est la fonction caractéristique auquel vous pensez. Et donc, quand on regarde la fonction caractéristique et que on la développe, en fait, les cumulants sont exactement en fait, on regarde une fonction qui a un tout petit peu... C'est-à-dire qu'en fait, la fonction caractéristique, c'est comme une fonction de partition, sauf qu'on la biaise un tout petit peu. Donc c'est la généralisation, c'est-à-dire que quand je regarde la fonction caractéristique, j'ai un paramètre en plus, en fait, et donc dans cette série, j'aurai un paramètre en plus. Mais c'est pareil, c'est les coefficients du développement en série de la même chose. C'est le log de l'espérance du moment exponentiel.
Une autre question ? J'arrive.
Merci. Donc là, tu disais tout à l'heure que c'était lié à des gaz, au scaling des gaz, et donc j'imagine que tout ce que tu as montré, c'est lié à la modélisation des gaz ?
Oui, alors disons qu'il y a deux niveaux. La modélisation des gaz, c'est la partie plus dynamique. Après, on peut regarder aussi des gaz à l'équilibre. Mais oui, on regarde beaucoup ces problèmes-là. Donc là, c'est le cas le plus simple, je dirais, dans le cas statique. C'est le cas le plus simple, c'est-à-dire le cas où l'interaction se fait juste par contact. Et après, il y a évidemment toute une littérature plus compliquée, même dans le cas à l'équilibre, quand l'interaction, par exemple, se fait avec des potentiels en 1 sur x carré. Ou, voilà. Donc il y a vraiment une grande littérature, à la fois côté probabiliste, côté physique statistique, sur ces questions de fonctions de partition. Après, en fait, cette fonction caractéristique, cette fonction de partition, elle sert aussi à caractériser les grandes déviations. Donc voilà, c'est tout un grand pan des probabilités. Ici, l'ouverture que je proposais à la fin, c'est l'extension de ça dans le cas dynamique. Donc le scaling n'est pas le même. Hein. Là, on avait vu que le scaling, la transition de phase qui est attendue dans le cas stationnaire, c'est quand le nombre de particules fois leur volume est de l'ordre de 1, ou 1 sur E. Évidemment, dans le cas dynamique, on voit que deux particules, elles n'ont pas besoin de se toucher pour se voir dynamiquement. Il faut juste qu'elles soient dans un même tube, en fait. Hein, si j'ai deux particules qui sont là, dans le cas statique, pour qu'elles se voient, elles se touchent. Okay, mais en fait, dans le cas dynamique, pour qu'elles se voient, il faut que quand je remonte ici en temps, elles se touchent. Et donc, je trouve en fait un cylindre à chaque fois. Et donc, la taille, le paramètre de dilution, c'est plus mu fois epsilon d, c'est mu fois epsilon d moins 1. Et puis, évidemment, c'est plus compliqué parce qu'il faut prendre en compte le temps. Et puis, au fur et à mesure que tout le monde bouge, quoi. Donc, il faut attraper le truc avant que tout le monde se soit défilé. Donc, voilà, c'est un petit peu... c'est plus... voilà, ça demande d'inventer d'autres outils, mais en même temps, même s'il faut inventer d'autres outils, il y a quand même quelques fondements de la théorie de la physique statistique, et notamment toute la partie combinatoire, c'est la même. Donc il faut comprendre dynamiquement les corrélations, ça c'est plus compliqué, mais la partie combinatoire, c'est la même.
Ok, s'il n'y a pas d'autres questions, je propose de remercier encore une fois Laure Saint-Raymond.